Thank you for coming. There are several interesting talks in this slot, so it's a great privilege that you've chosen to come to this one. My name is Jonathan Henson. I'm a senior software engineer at Amazon Web Services, and we're going to talk today about the design of the AWS SDK for C++ and some of the things that were challenging and some of the things that were successful, and some of the things that are also even a bit naive, as I allude to in the title. When we first began noticing that C++ 11 standard was making its way into commonly deployed compilers, and with the release of Visual Studio 2013, I thought to myself, I have to find a good excuse to use this without any legacy cruft to slow me down. Just start with modern C++, cross-platform should be a bit easier, and let's see what happens. Fortunately for me, AWS was receiving a great deal of requests for C++ support. So we began talking to our customers, and what we realized very quickly is that we were talking about multiple domains, and many of them with seemingly incompatible design constraints, from video games to systems to mobile to embedded in devices, and we had to find a way to meet these design requirements and still provide an idiomatic C++ interface. And we knew that we were going to have to spend a great deal of time up front thinking through how we were going to address these design requirements and have a flexible library for later on. So our agenda today for C++ engineers is we're going to go over each of these design requirements, or many of them. For each one of those, we're going to talk about the design decisions we made, the results. So we're going to look at some consequences, largely what was successful, what was challenging about that, and then we're going to have some recommendations. And some notes on these recommendations. I know we're all a little bit rebellious being C++ engineers. These are not mandates or even necessarily always the best practice. They're questions you should ask yourself in the design phase. And if you come to different answers to those questions, that's great. Just ask the questions. So before we go too far, let's dive into exactly what is the AWS SDK for C++. It's an open source library that does pretty much everything you need to do to connect to Amazon Web Services. Each of our 70 plus services, however many there are at the moment, there's a lot. It's cross-platform, it's modularized. We have a core runtime that we hand code. We have high-level libraries that we build to do very common tasks, such as uploading directories to Amazon's simple storage service, or uploading large files and doing it in parallel. And then the middle part are the generated SDKs. Amazon has an interface definition language that we, on the fly, generate the part that you would most likely interact with. So the S3 SDK or the DynamoDB SDK or the SQS SDK. Those are all generated on the fly. So our first and foremost design requirement is that it was cross-platform. And this meant that we are going to need to support Linux, both RHEL and Debian variants, as well as some, vintage Linux distributions, as well as the more modern ones. We're going to support Windows Desktop and Windows Mobile, Apple, so iOS, OS X, Apple TV, Apple Watch, and so on. We want to build for Android as easily as possible. This one turns out to be quite challenging. And then we want to have at least hooks to handle embedded systems where we cannot predict what the operating system is or what types of libraries are going to be there for cryptography and things of that nature. And lastly, we knew that we needed to support video games and therefore video game consoles. The first design decision here, and this is more of a meta decision, is to start and commit. So we don't want to do a prototype and have it running on Linux and then say, oh, wow, this was really useful, this is really successful. Now we need to get this running on Windows because that's a recipe for disaster. You really need to, we decided we wanted to think about it up front, every decision we made, every dependency we took, every interface gets scrutinized for how is this going to scale when we realize we missed a platform, or when Linux changes out from under us, or anything of that nature. How are we going to handle that? So the first thing that you usually need to decide when you're writing an application is how are we going to build it? How are we going to expose this to our customers? And another thing to take into account when you're writing a library is every decision you make that is in an interface that a customer touches is a decision you've made for the application. And it may be a decision they don't want. So we don't want to make a decision for what your build system should be. And we also want it to run across multiple platforms. So the easy decision here for us was to use CMake. We didn't have to maintain multiple Visual Studio solution files for multiple Visual Studio versions. We didn't have to maintain AutoMake files or Xcode projects or any of that. You code up what you need in CMake, you let it generate the solution or the build script, and you just run make, you just run MS build, whatever it is. And so that was the idea we were going to go with. And this makes it really simple to not compile things that you know are of no use on that platform. So we weren't going to compile libcurl or OpenSSL on Windows, or OpenSSL, we weren't going to try and compile that on Mac. We can compartmentalize out the parts of the build that are irrelevant to that platform in CMake. So that's the choice we made. How did that turn out? Most build systems just worked out of the box, and that is exactly what we were going for. We never needed to touch a Visual Studio solution. We never needed to touch a make file. Even the ones we didn't test with, such as Xcode or Android Studio or Qt's toolkits, just worked. And if they didn't work, it was easy enough to shim together. Custom platforms via toolchains. We have platforms we can't publish in open source, and we can't write the builds for lots of reasons. And all we had to have was a separate repository, a toolchain file, and the build just worked for those platforms. Target exports help tremendously with C flags and library linker flags. And it helped a lot when exposing these to the customer. Now, where this was challenging is that the deployed versions varied widely, especially on Linux. And going to our customers and saying, I'm sorry, you have Red Hat 5 and it has an ancient version of CMake on it, you can't use our product, is not a great option for our customers. So that was a challenge we had to address, or live with, however you want to look at it. Because of that, modern semantics were not always available, so we didn't get the nice and tidy target exports that we've come to expect in CMake. Another thing that we thought about a bit, but we realized how important it was after the fact, is to think hard about the "but I don't use CMake" experience. What if your user is using Visual Studio? What if they're using directly? What if they're using VC package? Or what if they're just writing make files with package config? How do we integrate with that? So that's another challenge. So here's one of the consequences, is you can make a really nice CMake experience for your users. And in this case, we simply call out define package for the AWS SDK. It defines a bunch of macros for us. It defines a bunch of variables. We even could write our own custom macros where you could say, hey, I want to use the S3 encryption client. And it would figure out that you need S3 encryption. It would figure out that you need S3, KMS, the core runtime, figured all of that out for you, and just passed it to your target link libraries call. And most of this is designed for you. There's been some excellent talks this week on CMake, so I will actually move on past this because there are better experts on this experience than me. But our recommendation here is to just use CMake if at all possible. It's less work for you. It's a better customer experience. We have not had any of our customers complain about CMake as a design decision. The target exports, there was a best practices on CMake talk yesterday. I encourage you to look it up. Use them. They're fantastic. But think really hard about how is it going to work for someone that doesn't use CMake. How are they going to get your binaries? How are they going to look up your CMake files if they're using CMake? How are they going to specify the linker flags and the include paths? Figure all of that out and have a good story for it. The next decision we made, that I've already alluded to, is to baseline on C++11. We're not including this into a legacy code base, so we had free reign on it. And the main goal here was that we can take advantage of things such as standard thread and standard mutex and standard atomic that are painful to implement manually. And this saves us time. This makes it far less likely that we're going to screw it up. The memory model is also really attractive. With shared pointer and unique pointer and R values, we don't need to spend near as much time thinking about the ownership model of our classes. We don't have to scratch our heads and draw it out on a whiteboard how the handoff is going to happen from two modules. A lot of that is taken care of for you. And clocks are painful. I don't know if you've ever tried to implement a clock manually, but it can get really tricky, especially when you go cross-platform. So standard chrono in the entire namespace is very attractive for us. And so we're going to look at something here that probably every one of you have written at some time in your life. I'm not claiming it is a perfect implementation, but try and imagine here how you would do this pre-C++11. So here we have a thread task that lives inside a thread pool, and it simply runs in a thread, grabbing as much work as it can off of the pool and executing it. Immediately here in the header file, we're using atomic, and we're using standard thread, two things we didn't have to implement. And then in our implementation, we've stripped out a bit to try and make this more slide readable, but you loop over while continue, check the executor, see if it has tasks, read everything you can as fast as you can, execute the function, hit a semaphore, which is sync points and standard conditional. We have a unique lock here. All of these are C++11 features, none of which we had to implement. It takes 15 minutes to write this, and we never had to go through the pain that we used to would have had to have done. But there's a dark side here. So this is a function that we added to verify that a DNS label was valid. Can anyone tell me what's going to happen there at runtime on GCC 4.8 or older?
Nothing whatsoever.
Worse. Something worse, much worse.
Exception.
Yes, or it will segfault, or it will crash badly. So, and you don't get an assertion, you don't get anything at build time. All you get is a complete failure when the user runs this code. You could argue that, well, that's the cost of innovation and live at the head, but we can't make our problems the customer's problem. We have to find a way to work around these things. So one of the design consequences here is you have to be really careful on some of the features on older, almost C++11 compilers that customers are going to use. So this worked well. As we already talked, we had far less to implement on different operating systems. Microsoft Visual C support was consistent. The only drawback was on Visual Studio 2013 and auto-generated move constructors and operators, which you find out usually when a build fails. Clang support, we had no problems with Clang. Modern features cleaned up the interfaces. We didn't have to have clunky ways of exchanging shared features and moving them around. And the defined memory model just made most decisions really easy. Where this was hard, Linux GCC is really, it's a special case. And sometimes you can't even upgrade the compiler safely. Where you can update the compiler safely, it's not, well, you can't upgrade it safely unless you rebuild the entire thing. And so that's a bad customer story. Integrating with legacy applications. What if somebody wants to use Amazon Web Services from their application and they've got a crufty old system that was built with GCC 4.1.2 on Red Hat 5? What are you going to do? I'll skip over this. I'll go to the last. Many of our users hated our exposure of standard IO stream. And I kind of like it, but I understand why users hate it, and so this was another thing that proved difficult. So some recommendations here. Do you need to support older Linux distributions? If your answer is no, you're done. Don't worry about it. If your answer is yes, we're trying to provide a feature that enables an entire business to have a capability, then you need to think really hard about how you're going to do that. What about the embedded story? Sometimes you don't get a full C++ compiler even there. The standard lib. We had great success using the standard lib. Most of the previously hard things are done for you. It's less to code, less to think about. My one thing I would throw out there is talk to your users about standard IOStream before you expose it. Because once it's in your interface, it can't come out without a breaking change. So just, it's not wrong to use it, but talk to your users. And take advantage of the memory model. We'll come back to that in a bit. This is the decision that I would argue has worked out probably the best for us. And if you look at just that slide, you'll see it seems somewhat inconsistent. But it's not inconsistent based on our philosophy, so I'll tell you what we mean. So the idea here for no dependencies is to use the operating system distribution and to abide by what I call the first boot rule. So on Unix, this means libcurl for HTTP, OpenSSL's libcrypto for all of our hashing and symmetric crypto, things of that nature. Use POSIX for operating system specific features such as file access, directories. A lot of that goes away with the latest technical specifications on file systems. On Apple, it's similar. We just used common crypto instead of OpenSSL. And on Windows, we had far more options. We used WinHTTP on most builds. For Universal Windows platform, we could use IXML HTTP request 2, which is a COM interface. bcrypt is the cryptography API that you get on Windows, and then the Win32 API for most file system functions. And then we decided to manually implement utilities such as datetime, on top of standard chrono, of course, logging, string split. There's been a lot of talk about string splits this week. Base64 encoding, hex encoding. Most of these things take 30 minutes to write and write a unit test for it and verify it's correct. So we just went ahead and bit the bullet and did it there and decided a dependency was not worth it. So how did this work out? So this is our build pipeline. And it's really complex and it's really long, and this is for only one of our consumers. But this is in AWS code pipeline, and we consume our source. First thing we do is we kick off our mobile platforms. So we have Android and Apple, various permutations of that. When those finish, we go to the desktop platforms. So multiple versions of Visual C, multiple versions of Linux, multiple versions of Clang on OS X, and we build all of these and aggregate them through. And what's beautiful about it is we don't change anything in the CMake script. It is just CMake, make, or CMake, MS build. It all just orchestrates, and it worked out really well for us. Builds for custom platforms also ended up working well because we don't compile things that we know will not work on that platform. We don't have any build breakages. The user is just responsible for injecting their interfaces at runtime, and we'll get to how we do that in a little bit. There was no surprise behavior that wasn't a bug in our code. How many times have you gotten almost to the finish line, you're a day before release, and oh, the XML parser in .NET makes some weird assumption, or the runtime library in X, Y, and Z does something weird, it breaks our entire system, we didn't know that was how it would work, and you're 2 weeks late shipping, or you make some really ugly hack in your code. We didn't have any of that. Legal and licensing was dead easy because we didn't have any legal to worry about. And where this was hard is not because of no dependencies, it was because we didn't take it far enough. libcurl causes us a great deal of complexity on both iOS, Apple TV, that sort of thing, and Android. And there's behaviors in libcurl that we don't want. We'll come to those shortly as well. And because of that, Android and iOS still have needed work. And that's the only place where I think this didn't work out well for us. So recommendations. I want to make a distinction between a library and an application. In an application, usually you know the target, you know the host, you often know the operating system, you know the memory constraints, you know the threading constraints. You can make these decisions and you have the knowledge necessary to make a good decision about a dependency. In libraries, every decision you make for the application. And if you take a dependency, every decision that dependency makes is made for your application. And given the various use cases we had, that was just not an option for us. So you need to think about that. What are the decisions that you don't want to make for the user? This involves threading, memory. What about exceptions? Now, the first boot rule. What's the first boot rule? I think it's pretty easy to explain. If it's on the machine, the first time you boot it up, you can consider it for a dependency. And that's the rule. If libcurl is on there and OpenSSL is on there, have at it, consider using it. But if it has to be pulled down from a package manager or something of that nature, unless you are internally in your company have a way to solve that problem in non-MP hard ways, then first boot rule. And just a quick reminder, I know we all know this, but dependencies don't always save you time. As I mentioned, hidden features, and then there's security and patching. So, avoid deep branching dependency trees. Your dependencies have dependencies, and that's unmanageable. libcurl is an excellent example of a beautifully written library. It's been wildly successful. But on different platforms, it links to GNU-TLS. On different platforms, it links to OpenSSL. On different platforms, it links to Darwin SSL. These things get out of hand really quickly, and it makes assumptions about your I/O model. And it gives you ways to plug in, but it's really complicated. And so deep dependency trees can be very bad for your library. How is this dependency that you're considering built? Can you embed it? Can you just put it as a header file inside your project and namespace it and then use it that way? That could be fine. Does your company have a build solution for native code? If they do, it may be a lot less to worry about. We'll skip on down to how do you patch. What happens when a zero-day vulnerability comes out in whatever you're using? How are you going to get that fixed on the user's operating system? What's the thing you're going to trust? Right? On Windows, usually that gets updated by the Microsoft team. On your Linux distribution, usually that gets updated by Red Hat or Ubuntu or whoever's doing it. But who patches it? How is it deployed? These become more complex when you have a dependency that is not part of the operating system distribution itself. And just remember, as a general rule, every barrier a user has to building your library is a barrier to people using your library. Another portion of the node dependencies design was just calling the OS APIs directly instead of taking some other dependency to do it. And this worked out well for most common platforms. The build was simple, bugs are easy to fix and ship, but there is one thing that makes it hard. So this code here is part of a directory traversal, and you'll see that we call readder on a string right here. And then we evaluate the enum dtype to figure out if it's a directory, symlink, or a file. And that's all the way down here. Any of our file systems experts know why this is wrong? It's not portable? Yeah, it doesn't work on Windows. Right, well, this would never get compiled on Windows. But yes, very true. Neither did we, because you would have to read very deep down into the Linux man pages to find out that not every file system module that's part of the kernel will give you the enum on directory type. So we wound up with some very hard to diagnose bugs. We had to introduce lots of logging to figure out what was going on this one user's unit test on this one variant of CentOS. So you actually have to call ls or lstat before you can do any of this. And it's technically in the man pages, but it's really easy to miss. So the advice here is the Linux man pages are your friend. If you go down there, you really need to almost memorize those man pages, have very strong code reviews by a Linux expert. So where this was hard, mobile persistence layers, and this was a complete miss that we had to go back and fix a good deal of. Most of the time on a mobile application, you don't hit the file system directly, ever. Unless you have a very special use case. The security is complicated, and usually there's a persistent system such as some fancy hash map or some SQLite mechanism where you go to persist your data for the application. As I mentioned, variance on POSIX file system implementations is challenging. Windows and Unicode, I could go on forever on Windows and Unicode, and I don't think we have time. So we could talk about it afterwards. But you need to make a decision about this ahead of time. So as I said, think carefully about mobile. Think carefully and read the man pages in Linux. And decide on Unicode before you start coding. If you're going to touch the Windows APIs, are you going to expose widechar? We decided not to. I'm not saying that's the right answer or the wrong answer, but if you do that, then you got to say, what do we do with the Unicode-only APIs? How do we handle conversion for the user? What about the if-def Unicode defines on getObject when you have S3 functions that are publicly documented as getObject? So how are you going to handle this? Have a story for it. Allocation control came directly from our systems developers that were in highly threaded environments, as well as our video games programmers, where it was not an option to touch new or delete. And it was not an option to override new and delete globally. And that's a really complicated problem. I'd love to talk to you about this afterwards if you have questions, but we couldn't do it. Also, there's potentially more performant heap allocations out there that people want to use, such as dlmalloc. The list could go on forever. Or you may want to do pre-allocation of pools and have stack pointers moving around based on the various types. So the different types maybe could go to different allocators. So global new, and global delete, or malloc and free were not an option. So how do we handle this and still provide an idiomatic C++ experience? So our decision was to write a memory interface, which we'll look at in a moment. And internally, we would always go through this memory interface anytime we needed to allocate memory. We would default to malloc and free and in place new, and call the destructors manually and everything that goes with that. We would use the STL allocator hooks where they were available. And we would allow the user to turn the feature off. So if the user did not need custom memory allocators, then AWS vector is just a standard vector, and AWS map is just a standard map, and you could go on about your happy way using the standard C++ standard lib types and not worry about it. We also knew that since we were working on allocators anyways, we should check our memory in the unit tests and just be done with it. We don't need extra valgrind runs. We don't need any of that. Since we already have an allocator hook, we can track all of the memory and verify it as part of the unit test run. So here's how the code looks for the allocators. It's really simple. We simply call into malloc, which is a symbol that we define that the user can install in a factory in a different spot. We allocate the memory. We do in place new here. And then we return the constructed memory. Delete is very similar. If we just call the destructor and then call free. And that's all there is to it. It's a bit more complicated for arrays. I'm happy to show you that code a little later. And then to use this, if custom memory manager is not being used, we define an allocator as mapping directly to standard allocator. We're done. If custom memory management is on, we define an allocator that hooks into all of these things that we just described. And then here's a couple of the type defs or usings here where we define AWS map as a standard map using our allocator. And we can do similar things for shared pointer. But where this worked well for us, the applications that needed it loved it. It was super simple. They wrote a single interface, injected that into the SDK initialization, and it worked, and they had complete control over their memory most of the time. Unit tests verified memory usage. We would have, say we have an engineer make a commit to the repo, push it up, we run our unit test, immediately they fail, we know that we've got a memory problem. STL integration worked well most of the time. There's some complications with standard function, but this is going to get better with C++17, so we'll look at that a little bit later, how we can do that. This had minimal impact on customers not using the feature. If they didn't need it, they just used standard C++ types. Worked very well with standard shared pointers since it stores the deleter, and we had a unexpected benefit, and this helped tremendously with DLL safety because we essentially forced everything through the same allocator, so we didn't have a problem with multiple heaps on Windows and DLLs. And this was a side effect that I did not even think about ahead of time until we noticed it. Where this was hard, it changes the ABI. This one feature will essentially change what a standard map, what an AWS map, whether it's a standard map or something different. The initialization scheme installed global state, which is bad, and there's more reasons why this is bad we'll come to shortly. OpenSSL and COM don't provide simple memory hooks. So there's memory that's just lost that the customer has no control over. STL type confusion, we would have customers passing a standard string, and then in GitHub sending us a linker error that could not tell that the linker error was because the types didn't match. So this was painful for our customers sometimes. The init and shutdown sequence, I'm going to show this on a later slide. Another unfortunate side effect is we could never accept or expose a standard unique pointer to a customer because the allocator gets lost. So recommendations here. If you're a library, consider providing a flexible memory model. If you allocate any memory and you have applications using you that you cannot predict, then I would argue it is your sacred duty to provide them control over how the memory is handled. And if you choose not to provide it, just check with your applications. Ask your users how they're using memory, what are their constraints. Are global new and delete sufficient? Standard unique pointer becomes available. It's a simpler way to do it if that's sufficient. Is C++17 an option for you to baseline? Then the memory resource is a great option here. For the sake of time, I'm going to skip on down. Do you need to allocate memory at all? This is a perfectly valid question. Some of the best APIs I've ever seen will tell you how much memory they need, and then you allocate it, and then you pass it to them. That's also a very valid option. So part of the allocation strategy ties in here to the customizability. Since we cannot predict all of our platforms, and since we cannot predict all of our build types and all of the customer's needs, everything that did anything substantial needed to be customizable. And then with sane defaults. So for platform specifics, we would use the OS APIs, but usually provide a hook for you to do something different if that was not available. We would use the principle of not being surprising. So if an interface has a name called executor, it's a thread executor. Do what people expect thread executors to do. Allow the user to control the behavior. And the benefit here is simply that if you make an assumption and it's wrong, it is easy to undo that. It is easy to undo it if you put it into the right customizable framework. So the first decision here was to use runtime polymorphism for this. I'm not going to bore you on Gang of Four style data structures and all of that. I'm assuming you all know how object-oriented programming works. So I will fly through this. We would use polymorphism and abstract factories. All if-defs get hidden inside a default factory where we kind of join everything together and figure out what got compiled, but they would not be scattered all over the code. And then we would expose a factory interface to the user so they could pass us a factory if they don't want to use the default one. So for example, we need to do SHA-256 HMACs all over the place. Here's an HMAC interface. It calculates a hash result based on a secret and the actual thing that you want to sign. Here's the factory, which returns an instance of SHA-256 HMAC. Oh, this is the abstract factory. It returns an instance of HMAC. If you want to implement a SHA-256 bcrypt, you would just implement this. And then here's how the default factory would work. We have the default SHA-256 HMAC factory. If we're using Windows, return the bcrypt one. If we're using OpenSSL, return the OpenSSL version, common crypto, so on. And that's all there is to it. Then to allow the user to override this mechanism, if we got it wrong for some reason, you don't need to do anything fancy. Just give them a standard function they can set and call it at a later time. So you pass this into the SDK options. When we get ready to start computing SHA-256s, we'll call your function, get a factory back, use that for the rest of the application. So the consequences here. Cryptography in HTTP 1.1 worked great. Where our users hated curl or didn't want to use it, they wrote their own. Where we actually had a case where a user was writing networking hardware and had hardware-based crypto, where they would go directly to the board to do these things. They did not even tell us they were doing it. They didn't ask us how to do it. They just did it. And then in a meeting one day, they told me they had done it. And that was really exciting. And they were able to extend this simply, especially adding new platforms. Right after we launched the SDK for developer preview, we started getting build failures on Mac because OpenSSL had been deprecated. So about 6 hours later, we had common crypto plugged in and it was finished. It was really simple to fix our mistakes. Where this is hard, the factories, due to some other constraints, were getting installed into the global SDK initialization state. And this has special problems whenever load library comes into play or whenever you do not have complete control in your library and the application cannot know that it is using the SDK. Global state gets really hard. We couldn't help it because OpenSSL forces you to use global state, and it all went into global state. We'll have a recommendation on this in a moment. Not all C APIs map well into C++ classes. So bcrypt is a prime example. If you've ever looked at the AES CBC implementation in bcrypt, it is really hard to make that work in a C++ init, update, finalize sort of idiom for crypto. We have one. If you want to know about it, we'll talk about it later. And it forces more heap allocations, and you have the overhead of the dispatch that comes with runtime polymorphism. So this is definitely something to consider before you make that decision. So our recommendations are, if it's possible, take advantage of inheritance and polymorphism. It's there, it works, it's usually performant, and the heap allocations aren't a big deal if you initialize them at the right time and don't hit it all the time. Think carefully about your C, API, and init calls. Where's that state going? Ideally, you could encapsulate that into a library handle or some sort of state that is per instance of the library. That's not always possible, but think through if you can do that. Don't get fancy with your factories. They don't need to have complicated abstract factory hierarchies and multiple inheritance or whatever weird things people do with factories. You can just take a function pointer and use it. So for the things that were not platform specific, such as threading, so an executor interface, the design decision was just default the standard thread with an optional pull. That's what I would expect if I was the user and I saw that title. Memory allocators, we already talked about using default, malloc, and free. Also what I would suspect you would want most of the time. And then all interfaces, all custom things that do any task within the SDK get injected, either via constructors or client configurations or in the global state for the SDK init. So it's simple for users to override this behavior. So for the client scoped changes, we have a retry strategy which figures out when to retry an error, if it was a network timeout, whether the service had the problem or the client had the service, does exponential backoff, that sort of thing. A thread executor, a rate limiter, which allows, say, a video game to say, hey, I'm using all of my bandwidth for this multiplayer game. I really need you to stop uploading that data to simple storage service, or I need you to do it a lot more slowly because I need the bandwidth, so that provides them a mechanism to do that. And then for the more global options, that should be SDK wide, so not scoped to a single client. There would be logging options, memory options, HTTP, crypto, so on. And here's an example of one of them with memory options is we just take a pointer to a memory manager. Done. So where this worked out well, customers rarely ever used it, which means, I think, the defaults were good defaults. Singleton support, and this one's kind of weird, but suppose you're in a constrained threading environment and you don't want 10 threads across multiple clients running. You're in a video game engine and you have 2 threads available for I/O, and that's all that should ever be used. This allows you to pass the same thread executor to all of your clients and be done with it. Custom platforms, once again, they're manageable. If we didn't write the right implementation for that platform, it's easy to fix that mistake. Testing was really easy because we just stub out the interface and pass an instance to the constructor, and we can verify the behavior goes through the interface properly. And because of this, this results in cleaner interface separation, smaller classes. Where this got really hard is ownership and scoping complications. And we'll go ahead and cover this now. So we take an instance of a shared pointer for executor to possibly the same instance to an S3 client, a DynamoDB client, an SQS client, go down the list. What's going to happen here when, say, one of those clients goes out of scope or gets deleted? And they're passing member functions to it. If one of the clients goes out of scope and it's scheduled a task on that executor, then the executor picks it up and starts running, but now the object is gone from the history of the universe, and you will immediately segfault, right? You can work around this, obviously, and you can tell your users to do smarter things to handle the situation, but it's something that is a side effect of the customizability approach we took. And every virtual function you put anywhere is now an expanded API surface, and it's expanded blast radius, and it's often easy to forget this. So some recommendations here. Default to the least surprising thing. What does the user expect an interface to do? And do that. Consider constructor injection, rather even than using a giant struct to pass a bunch of pointers to it. It will make the bloat obvious. It's idiomatic to resource allocation is initialization. It can make bad code look bad really quickly. Think about ownership ahead of time. This was a mistake we made, at least in not documenting that that's how that would work. Who owns it? Am I using it that way? Am I encouraging users to use it that way? And then, oh, go ahead.
I'm sorry, would you be able to provide a bit more concrete example of what you mean by constructor injection?
Yes, so as a constructor argument, take a shared pointer to an interface.
To something that thing needs.
Yes.
Right, to do its work.
Yes.
Okay.
Virtual functions are APIs. Anywhere you put virtual, a user is going to override it and implement that. If you ever add virtual equals 0 and then push up to GitHub, then you will have those customers breaking immediately. So remember, you're increasing the blast radius every time you do this. This is our most contentious design requirement. And yeah, we couldn't use exceptions because video game engines, most of them forbid it entirely. Legacy applications that aren't exception safe, forbid their use. Those two go together. So what was our decision to do this? How are we going to handle it? Well, we stole outcome from Erlang, essentially, and used that. And it's just a union of return type and error. This actually gets a bit easier in C++ 17, where you don't need this at all. So I would recommend actually looking into that. We decided to log very heavily. Constructors don't do too much, and force allocations up to the user where at all possible. And that's the best we could do. Put a Boolean operator on it and say that initialization failed, and that's what we got. So here's a brief snapshot of the little wrapper around the exception union, or the outcome union. So what were the consequences here? Where did this work well? Well, we don't make that decision for the user. So if the user doesn't want exceptions, they don't get them. User wants to throw exceptions, the SDK is exception safe, sort of, they'll be fine. And this supports more customers. Outcome worked out nicely. It made for nice and tidy code most of the time. We never had to have the religious zealot argument about exceptions because we simply said our customers, not all of them can support it, it's not an option, close the book, it's finished. And more recently, it makes the move to async event-driven I/O far simpler. If you just wean yourself off of exceptions now, when you go to an event-driven architecture, you have, I don't know, 2 function calls and a stack trace anyways, so how's it going to help you very much? But there was one challenging part. This is a curl callback to read the body that curl calls when it's ready for some data. And so we read from the I/O stream the amount of data they requested. What could I/O stream do? Anyone? What could it do? What's something it has the option to do right here? It can throw. And I/O stream can be overridden with your own stream buffer, or if you're really brave, your own I/O stream subclass. And if you throw here, what's going to happen? This is 5 or 6 functions down inside libcurl. What's going to happen to all the memory curl allocated? It's gone. Well, who knows? Well, it's not gone, but you don't have any pointers to it anymore. It's done. So while our C++ code was exception safe, the callbacks from the C functions were not exception safe. So where this turned out hard, outcome bloated binary size, that ship sank in the harbor years ago on binary size anyway, so I don't know, that's the end of the world. But you never can turn them off on some platforms, so say on Windows, you can't make it not throw, as far as I know. How are you going to handle out-of-memory errors without exceptions? If you're using the STL types, so if standard vector and you run out of memory, what's going to happen? If you're not getting the out-of-memory or the bad alloc exception, how do you know? How can you do something reasonable about it? This is more of a complaint, but RAI becomes technically unsafe, and you end up with assert all over the place, and you end up with Boolean operators sitting around to say that, yes, I allocated all of the things I needed in this constructor. You can go ahead with your, it's fairly standard idiom in C++ anyways. Polymorphism-based APIs, as I just showed you, used in C callbacks. That one will definitely bite you. So recommendations on exceptions. These are questions you need to answer as you're thinking through this. What about out-of-memory errors? If the program can just crash when it's done, fine, who cares? Don't worry about it. If you're somewhere where you have your memory very well segmented and you're using the allocation strategy we showed before, then out-of-memory is usually a perfectly handleable thing. Drop some textures or load the lower res textures, or there's a whole, change how you're communicating, how frequently you're calling out to another service. Can they be trapped behind a compatible ABI? Can you put a C wrapper around it? What about load library? If it can be detected at debug time, assert's an option. So do you need to throw an exception here anyways? Be extra careful when you touch the C APIs, as I just showed you. And consider providing and committing to providing object validity checks via Bool operators seems to be the common way of doing it. Our last design decision here that we're going to talk about is the threading model. And this is one that I think you really need to think very deeply about if you have the default idea that I had. We chose to base the asynchronous APIs on the synchronous API. And we did this for a couple of reasons. One, it was simple to reason about. You just submit it to a thread executor, let the thread executor run it asynchronously, return to the user when you're done, call a callback, give them a future, whatever you want to do. And most of our core code was already stateless, so thread safety was going to be a bit easier to pull off. So here's how this ends up looking. This is in the Amazon Simple Storage Service client. We have put object async, which is what we expose to the user, that just submits a lambda to the executor, which calls a private function, the put object async helper, which you will see here, calls put object, and then calls the handler when it's done. And arguably, this is really simple to reason about, right? I just showed you this problem. So where this worked well, user can control the thread count. User has it's a simple model for people to reason about. That worked out well, but there's a lot where it's challenging and where it's perhaps a bad idea for your application. Shared memory is theoretically impossible to prove correctness between threads. Unit tests are difficult. You end up with a bunch of conditionals and mutexes and counts all over the place to synchronize things. Mutex on some platforms is a substantial penalty. On some platforms, it will flush you all the way down to RAM. So where these things matter, you are basically, the moment you make this decision, you are tying your customer in to this decision. Blocking I/O is an efficient use of the networking interface. It consumes substantially more CPU when you start doing sleeps to handle it. Changing to non-blocking I/O would break your interface. So if you ever say, hey, C++17 has a new technical specification for networking, I'd like to use this. You can't, because you've made decisions here that will, at the best case scenario, is going to decrease the efficiency of your code substantially to adapt to it. And some applications only have a few threads available. Let's go back to game engines. What if there's only one thread? So you've made it non-blocking from the user's perspective, but you may queue up 100 web requests, all of which have to wait for the other one to finish before they can execute. So my recommendation here, start with your I/O model and work backwards. And your threading model may just work itself out. Instead of thinking procedurally and about your algorithm, if you're going to be I/O bound, start with the I/O. Start with epoll, start with IOCP, KQ, whatever it is, or start with the new C++17 spec on this and work backwards. And then, while you're doing this, you may realize there's no need for the shared memory to begin with. If you go to an event-driven framework, or you go to a callback C-style thing, or coroutines, there may be no need for you to ever share memory between threads. You might need to hand them off between threads. You might need to do some trickery with pipes, but at the end of the day, you may never need to even share the memory to begin with. And if you forbid blocking, then this becomes super easy to do. And then build your synchronous API on top of the asynchronous one. It's perfectly legitimate that customers want a synchronous API. They want to think procedurally. That's fine. Let them make that decision, though. And they could use coroutines. They could use standard condition variable. Condition variable is simple, easy to test with. And then, as I said before, what happens in a single-threaded environment? As always, thank you for coming to the talk. Please send us pull requests at our GitHub if you see any problems. And thank you for your time. think we have some time for maybe some C++ specific design questions if anyone has them. Otherwise, I'll be available around to talk afterwards.
Hey. Oh, sorry. Yeah, I had a couple of questions actually. First, I didn't really catch the reason why you use shared putter everywhere but not unique putter.
Yes. So with shared pointer, the allocator is stored. I'm not very good at templates, but the allocator is stored with the shared pointer that you specify, and it does not change the type. So you can pass a standard shared pointer back to the user, and it will keep the allocator that you specified. On standard unique pointer, it goes through the standard delete. We just pulled up the reference, so it would show it. But if you specify the allocator, it changes the actual type. You can use unique pointer, but you can't pass the standard unique pointer without the extra template arguments around.
Oh, okay. I think there are some options around that, but okay.
And if there are, I'll be happy to use them.
You can use the still function as the shared putter deleter.
I'm sorry, I can't hear you. Could you go to the mic, possibly?
You can use this do function as the share putter deleter.
Okay.
That erases the type.
Yes.
And my second question was about all the factories and pointers everywhere. I don't want to gain a bingo points for saying like it looks like Java, but was that really necessary to have dynamic polymorphism for something that depends on your architecture that's determined when you compile?
We don't always know those things at compilation time. So if we can't compile it, there has to be some mechanism for the user to inject it. I'm certain that there are some templates way to do things of that nature, but nothing's ever necessary. The design pattern to consider.
Yeah, but you're making everybody pay for virtual calls when you said 1% is going to use it.
You mean 1% is going to use the customization?
Yeah, and the 99% pay for what they don't need.
That's true, and that could be something to consider, ways to provide a zero-cost abstraction on that in the future.
Great, thank you.
Anyone else? Okay, I'll be sticking around for a while, so if you want to talk, let's talk. Thank you again.